The next type of ionic compounds we are going to name involve a transition metal. Transition metals are unique in the fact that they have more than one charge on their ion. So the name of the ionic compound has to reflect the charge on that specific metal cation, and we represent the charge with a Roman numeral. The Roman numeral gives you the magnitude of the charge on that cation. There are some exceptions to these naming rules. They are silver, zinc, and aluminum. If you have one of those metals in your ionic compounds, just follow the naming rules for group 1 and 2. So let's look at CuCl. Cu is a metal. It's found on the left-hand side of the metalloids. It happens to be copper. So we know it's a transition metal, but we have to follow the rules for our transition metal naming. So we have to use the charge of the nonmetal or polyatomic ion to determine the transition state of the metal. Our nonmetal in this case is Cl. Cl is in group 7 on the periodic table. Any element in group 7 on the periodic table will have a -1 charge on its ion. So now we have to use the formula here to determine what the charge on copper was. So we needed 1 chlorine ion, 1 Cl minus, to balance whatever the charge was on copper. So that must mean the copper simply had a charge of +1. Another way you can handle this most of the time is by reverse crisscrossing. So when you're trying to figure out the formula, you can crisscross the charges to make the subscripts for the opposite atom. Well, here you can go the other way. You can crisscross the subscripts to get the charges on the ions. So since both of them have a subscript of 1 basically, because there's no subscript, then we know copper is +1, Cl is -1. So that means we need to represent that +1 charge in the name of our metal. So we represent it with a Roman numeral. This is copper 1. Since we know chlorine is simply a nonmetal, we can follow the naming for that, and we just change the ending to IDE. This is copper 1 chloride. Our next example is MnO. When we look up Mn on the periodic table, we see it's a transition metal. It is manganese, so we need to follow our rules for naming a transition metal. So we have to use the charge on the nonmetal or polyatomic ion to determine the charge on the metal. Now this one involves oxygen. Oxygen is group 6 on the periodic table. Everything in group 6 has a -2 charge on its ion. We have to figure out what magnesium's charge on its ion is then. Well, if we only needed 1 oxygen to balance the charge on manganese, and oxygen has a -2 charge, then manganese must be able to balance that with just 1 ion, so manganese must be a +2. You'll notice here that trying to crisscross the charges won't really help you this time, because you'll end up getting a +1 and a -1, and that doesn't work. So crisscrossing doesn't work for this all the time, and this is an example of that. So anyway, we have manganese 2+. We're going to represent that 2+ with a Roman numeral 2 after the name. So this is manganese 2. Oxygen is a nonmetal. We change the ending to IDE, so it's oxide. This is manganese 2 oxide. Let's try one more. We have Fe2O3. Fe is a transition metal. It is iron. We have to follow the naming rules for the use of a transition metal, so we have to use the charge on the anion to determine what the charge on the metal cation is. So once again, oxygen is in group 6 of the periodic table, which means it'll have a -2 charge on its ion. Well, in this case, we need 3 oxygens to balance out whatever the charge is on iron. So if we have 3 -2 ions, we have a total negative charge of -6. Well, the iron ions have to get us a +6. Well, we have 2 iron ions. So that means each iron ion has to have a charge of +3. Because if you have 2 + 3 ions, you'd have a total positive charge of +6 to balance out the oxygen charges. So Fe is +3. You could also figure this out by just crisscrossing the subscripts. So if you crisscross the subscripts, you could see iron would have a charge of +3, oxygen a -2. Now we need to represent the name of our metal cation with the Roman numerals. So this will be iron 3. And once again, oxygen's a nonmetal, so we just change the ending to IDE, iron 3 oxide. We also need to be able to go from names to formulas, so let's look at a few examples of those. Now with the transition metal, it's very easy to recognize you have transition metal because you have the Roman numeral in parentheses. So you know it's an ionic compound because of the Roman numerals. You know it's a transition metal because of the Roman numerals. And you also know the charge on the metal cation because of the Roman numerals. So it's kind of helpful. You can see titanium is right there, a transition metal. So we're going to follow that path on our naming flowchart. So we're going to write down the symbol of the metal cation with its charge. So in this case, it's titanium, Ti, 4+. So now we're going to write down the symbol of the nonmetal or polyatomic ion with the charge. All the examples we're going to do in this video will be nonmetals. Sulfur is in group 6, so it has a -2 charge on its ion. So you can think about this and go, okay, to get a neutral compound, I'm going to need 2 sulfurs, 2 -2 charges to balance out the +4 charge. So the formula is TiS2. Or you can go the least common multiple route. So the charges are 4 and 2. The least common multiple of 4 and 2 is 4. So you need to multiply each of these ions so that you get a +4 and a -4. Well, to get a +4, you just need 1 titanium. And to get a -4, you need 2 sulfurs. These numbers then become the subscripts in the formula. So TiS2, because you do not need subscripts if you only have one of the ion. You can also crisscross here, but you got to be careful. If you crisscross your charges to make the subscripts, then you'd get Ti2S4. That would be wrong. You have to reduce that. Reduce the subscripts to the lowest ratio, you get TiS2, just like you're supposed to. Let's look at vanadium 3 nitride. Vanadium is a transition metal. The Roman numerals give that away. So we're going to follow the transition metal naming flowchart. We're going to write down the symbol of our metal with its charge. So that's V3+. We can then look up nitrogen on our periodic table. Nitrogen is in group 5 of the periodic table. Everything in group 5 has a -3 charge on its ion. So we have V3+ and N3-. You can just look at that by observation and see I'm just going to need one of each ion to balance the charge and make it neutral. So my formula is going to be Vn. Or you can do the least common multiple. The least common multiple of 3 and 3 is 3. What do you need to multiply each ion by to get a +3 and a -3? Just need to multiply both of them by 1. Those numbers become the subscripts, so it's just Vn. Crisscrossing will also work if you're careful. So cross the magnitude of the charge, and you'd get V3N3, which would be wrong, but if you reduce it, you would still get Vn. Let's look at one last example, lead-2 fluoride. So lead is a post-transition metal, but it still has multiple transition states. It's given away by the Roman numerals, so we're going to follow the transition metal path on our flowchart. We're going to write down the symbol for lead and its charge. So in this case, Pb2+. We look up fluorine on our periodic table. It is in group 7. So everything in group 7 has a -1 charge on its ion. So we have Pb2+ and F-. So you could look at that and say, okay, to balance this out, I'm going to need 2 fluorines. So the formula is PbF2. Or you could do least common multiple. So you have a +2 and a -1. So the least common multiple is 2. How do I get a +2? Well, I multiply Pb2+ by 1. And to get a -2, I multiply F- by 2. So those become the subscripts. My formula is PbF2. Or you could crisscross the magnitudes of the charges. The 2 on lead becomes the subscript for fluorine. The 1 on fluorine becomes a subscript for lead. And you get PbF2 without having to reduce this time. So that is how you name and find the formulas for ionic compounds involving a transition metal. Keep practicing so you can get better at these.